the reactor or the combustion chamber. And probably you're wondering, why don't we have a combustion chamber directly? Well, that's the point of knowing how to simulate processes. Many times in real life, something can be modeled with another thing. So for instance, this is modeling a pipe. It's transporting a material from left to right. Instead of actually using this pipe, we are modeling it. Why? Because right now we don't care about the size of the pipe, velocity, profile, if there is friction loss, and so on. So it depends a lot of what do you want to model. So for instance, this distillation column doesn't even ask you for what type of trays, how many tray spacing, and so on. So there are plenty of things regarding on what is your interest. So right now our interest is to essentially just model this process for material, energy balances, compositions, purities, and heat duties. Also the electric charges requirements. And here we go. So the combustion chamber, I'm going to be using a reactor because I know combustion chambers are essentially something that burns. And right now I have several opportunities. So because I don't know the kinetics of this reactor, I cannot use any of these three. I know the stoichiometry. Well, yes, I know that this is 100% combustion. Do I know the equilibrium conditions? No. So technically I can use this one right here and the Gibbs free energy. Actually, it will be kind of interesting to use the R Gibbs energy. But right now, let's stick with the simple one. This is the most common one you will be starting to use. So this one goes here. We need to add air. And see how this feed is required and you're not obliged to add it. Because this is an external or an additional. You can have as many as you want. And this happens in real life. If you have several inlets, let's say A and B, you can do it. That's no problem. And I like to have these in order to see that these are my raw materials. Combustion chamber. And this is another important part right here. I have this product or this water decant for free water or dirty water. What the hell is that? Make no worries. Right now we're not going to use it, but essentially is when you want to have a water stream from the, let's say, out of the organic material. So this product, let's call it stack. And let's click next just for the sake of knowing what do we need to fill up. And as you can see here, guys, we need to have heat duty of 0. Why are not we allowed to add a temperature? Because we don't know about the reactions. We don't know what is the temperature, and we are most likely not going to cool down or heat up this reactor. In real life, actually, what we want to do is to take advantage of the heat. This is done at 10 bar or 0 pressure drop, so you can select whatever you want. 10 bar. Let's do the 0 pressure drop for you to check this simulation. And the reactions are now the most interesting part right here. So let's check out the results of this stream and let's check out the mole fractions. Okay, so we got plenty of methane, some ethane and propane, some traces of butane, cyclohexane, toluene. So actually we have everything. The most correct thing to do will be to add all these reactions. So component 1 will be methane with oxygen. Produces, oh no, we have something missing. And yes, I did this on purpose. I want you to go back and see how can we add further data to our component list. So we know CO2, of course, we want to see that, and water. Let's run this part right here. Remember that whenever we add a component, we need to run the physical property environment in order to get the binary parameters, which I did already. And now we can go to the simulation environment and fully define our reactions. So we were talking about methane, 1, 2, and goes for CO2 and water. This is 2, no, well, 1 and 2. Fractional conversion, full conversion of methane. Next. And actually, let's check out all these individually because I don't remember that much the components. So let's ethane, oxygen, CO2, and water. And I know this can be a pain in the ass in whenever you're modeling, especially imagine if you have a crude oil and you will have infinity. We will see later on further courses how to model those type of reactions. Instead of we adding individual reactions, there are models that will simply verify the best equilibrium condition and minimize Gibbs free energy and obtain the result. It's 1,7,1,7,4,6,4,6 full conversion of ethane. And I love it. If you make any mistake on the balance, you will get it. So ethane, oxygen, CO2, water. 153, 153, 4. Now ethane, 2, 13, 2, 13. Butane is 2, 13, 8, and 10. 8 and 10. 1 and butane. We're almost done, guys. Be patient. Cyclohexane. One 636. 1636 of cyclohexane. Benzene. Oops. Almost done. 2, 15, 12. 2, 15, 12. 6 of toluene, no, benzene. Okay, toluene, CO2, and water. 1, 9, 7, and 4. Based on toluene. Next. Okay guys, so one thing I wanted to show you is that actually reaction 2 and 5 are not fully defined, and let's see what happens when that is the case. And we should find a material balance error because of the reactions not being balanced. So let's verify actually for all. So there's a warning on stream name air. I don't know why there's a warning, so let's check it out. Component moles are normalized in order to get the total mole flow. So that's a very common practice in Aspen Plus. Actually, this warning should not even be a warning, but is whenever you're adding a decimals and decimals that are either truncated or let's say rounded up or down, you will get either a 0.99999 or you will get a 1.00001. What Aspen does is essentially normalize that number into 1. So all the fractions will be divided by the fraction, and you will get a beautiful sum of 1. The same is true for the feed. That's fine. And we have an error. Those errors are actually very important. Errors means that the simulation failed, while warnings mean that you just gotta be attentive to that. So let's check it out. error in the combustion chamber. And yes, as stated before, guys, the reaction number 2 and reaction number 5 have some errors. So let's go and fix it by ourselves. So we got this part right here, C2H. Okay, so we have 2 carbons. This is the first error. We have 4 carbons, 12 hydrogens, 12 hydrogens, 14 oxygens, 8 plus 6 is 14. So let's change that. That should be 2. And that's what I actually don't like that much of Aspen Plus in this specific case. I would really love just to add this part right here and Aspen automatically doing the material balances. And if not, at least I will really love that Aspen Plus will tell me that the material balance is not okay. Now let's check for this one is okay, 6 carbons, so first things first, yes, 12 hydrogen, that's fine, and we got 6 plus 12, 18, so this gotta be 9 right here. Hopefully we are all set up. Let's run the simulation and see how it goes. There should be no errors and no warnings, and as stated, we do not seem to have that. Okay, so still we have those warnings that I was telling you about, but now we're fully defined and we are done. Essentially, that's what I wanted to show you. We are done with the process simulation. And now let's continue with the results. So I'll see you in the following lecture.